Good evening, everyone. So, sorry for the little delay. So, yeah, we will start the lecture today. So, yeah, again, in the first half, we will go through the concepts, and in the second half, we will go through the questions. So, just a little question, like, how many of you watched till week 2 lectures? Just raise your hand. I just wanted to know for my own. Okay, Billy has. Okay, Radhika and Krishnan. Radhika, just week 1. Okay. Okay, Radhika. Great. So, nice. And yes, so you have watched till week 3 or week 2 or let's say week 1. So please don't quit this particular course at the end, because most of the students generally quit. I don't know why, but yeah, yes. So this was a little motivation why to do this course, since it is related to mathematics and it will be useful for all subjects. And if you are planning for AIML, then definitely it will be useful. So yeah, moving ahead. In the week 3, Sir taught about the affine function, what are the benefits of affine function, and where affine function is used. So basically, I was going through the lectures today, especially robotics. Yes, very, very true. Robotics, yeah. So because in robotics, you will have the Kalman filter, state estimation, and even I also worked in robotics part. For example, you can have a SLAM. There also this applied linear algebra is used. So, okay. So, moving ahead, we saw what is affine function, and I hope you watched my week 2 lecture. So, I will not repeat. Since week 1, I couldn't see many people around me in the live session, but yeah, week 2, I could see many of you. So, yeah. Poonam, your video is on, so if you'd like, you can switch off the video. Yeah, sure. Thanks for joining. Okay, so moving ahead, we saw affine function. We saw that affine function can be written as ax plus b with the offset of b, whereas linear function doesn't have this offset. So the first equation states that this is followed in affine function provided this is applicable. So here this is the condition for affine function. Otherwise, if this is not there, then linear function will be there. Okay, the only difference between affine and linear function. And today's class we will see the affine function application in perspective of linear algebra. So yeah, so if it is a affine function gx, then there exists a matrix where we can write this gx is equals to ax plus b, and this particular thing is linear, and we are adding b offset that will cause it as a affine. So yeah, what is this? Suppose you have n nodes. Okay, n nodes in the input. So where n nodes is used, for example, n users. Nodes can be users, your nodes can be vehicles, node can be any quantity. Okay, and at the output you are getting y1, y2, ym. So you are getting these m outputs. Okay, m outputs. So this is mainly the basis for neural networks. It happens in neural networks. Neural networks, how many of you know?
I'm familiar with neural network.
Okay, very great. Okay, so yeah, neural networks are a deep learning network that helps in prediction of any feature. So it's actually a network where we first train a set of data sets. So this x1, x2, xn are data sets. Okay, for every data set, this will be a feature. Okay, so this will be a data set. Suppose 1, 0, 2, 3, 4, 1, 2, 3, 4. This is a serial number. So this many, suppose 1000, and then it will have these features, xn features, and with this feature you will train a network. Suppose any network which is one of the LSTM, then RNN, and many other networks are DL. multi-layered perceptron networks. So these are some name of neural networks. All comes under neural networks. Yeah. So in that you will have so many connections. So you can see every Y1. Guru Swami, your hand is raised. Do you want to say? Do you want to say anything? No. Okay. Yeah, okay. So the only difference between your sir video lectures and my live session is this is interactive since I am presenting live. So you can anytime unmute yourself and you can ask any questions. So yeah, so this is the output nodes. So what it is connecting with every features. So output is connecting with every features. So we are making it with respect to a weight. So suppose this is W11 x1 plus Wi 12 x2 W1n xn like that. This is I. So suppose W1 x1 plus W12 x2 plus W13 x3 so on. Similarly Y2. Y2 will be W21 x1 plus W22 x2 so on. So yeah, so this is, if you see, this is nothing but a inner product. Okay, so this you can write W tilde. This particular vector is a W tilde, where you can write as a W tilde transpose as W11, W12, I1I, W1n. So this is showing one is for one subscript first. Okay, so what we have seen, y is equals to this particular thing. But at the end, what you do at the last layer, you have to add some bias. Why bias is required? Because bias helps you to maintain the unit of every features. For example, you have one feature, x1. Suppose this is in some other unit and this is the other unit, kilogram, and then one is grams. So this will have some different unit by a proportion of 1000 because 1 kilogram is equals to 1000 gram. So at the end you add bias at every layer. Okay, so this one is added as a bias at B1, B2, Bm. Okay, every node will be added with different bias. So okay, so what you observe, this particular thing is nothing but a affine function. So this is layer 1, and at the end you pass it to a non-linear function to predict it some non-linearity in the network. So one of the example is the Rayleigh network. We will see what is Rayleigh network. Rayleigh network is nothing but tan h. So because if you can see, I'll not go through basically. So tan h is this one. So this is basically what it is. The output will be in this particular range. So that's why we pass it to Rayleigh network, or also known also sigmoid, also exponential. These are some of the example of some non-linear functions that is applied at the last layer in the neural networks. So yeah, this is a practical example. So similarly, we will see the practicality of everything of whatever we are studying in applied linear algebra in AIML. Okay, so this is just to give some understanding. So make you gives the flavor of it. So yeah, now sir also went through the convolution operation. So what it is, convolution, if you have seen, it is, if it is a linear system, HT, and xt is input, the output will be ht convolution with xt. Okay, this is continuous time signal. This is continuous time impulse function of the system, and this is LTI. Okay, the output is ht convolution with xt. And if you convert this into a Laplace transform or frequency transform, then definitely it will be coming hs into xs. If you are from electronics background, you might know about this. Okay, similarly in linear algebra also we will see the convolution operation. So what it is, it shows that if we have the a or b vector, then c of k at the k index, it will be ai bj such that I plus j is equals to k plus 1. Okay, we will see with example because when I saw also it was very confusing. So let's see, A is this vector and B is this vector. This is an R5 and this is an R3. So according to convolution, this shows that C will be C subscript this one. This is subscript for a vector. 3 plus 1 minus 1. 3 plus 5 minus 1, that is R7. Because this is written m plus n minus 1. Okay. So if C1 we will calculate, then I plus 1 is equals to K plus 1. K is 1 plus 1. I plus 1 is equals to 2. AI Bj. What are the possibilities where this I plus j is equals to? This is only one possibility, AI plus bi. AI into bi. Then A1 into B1, sorry. Then C2. I plus j is equals to K plus 1. K is equals to 2 plus 1, 3. So what are the possibilities for I plus j is equals to 3? A1, B2 plus A2, B1. Similarly, C3 is calculated. Similarly, C4, C5, C6, C7. Since it is from R7, so it will go to C7. Okay. So this is all
Ma'am,
about convolution.
ma'am, how that C4 comes, actually 2 plus 3 equal to 5.
Yeah, yeah, yeah.
So,
Yeah,
what?
let's see. C4. I plus j is equals to 5. Okay. AI Bj. So what are the possibilities where this particular thing follows? Suppose A2, B3. This is 5, fine. Then A3, B2. This is 5, fine. Then A4, B1. This is fine, fine. But why? Because B is only from B1, B2, B3. You have to check with the permutation and combination where I plus j is equals to 5. Is there any other thing that is leading to I plus j is equals to 5? It will,
Actually, in C3 there is I plus. Okay, ma'am. I got confused.
okay.
Okay, yeah, okay,
Is it
fine.
clear now?
Yes, ma'am. Yes. Okay, fine.
Okay, okay. Nice. So yeah, so this is what we sir was telling in the class is vector convolution is somewhat similar to polynomial multiplication. So he was giving with one of the example. So one thing which I like in this course is after every concept, sir is giving one of the example with it so that you can correlate and you can also understand. For example, if someone taught only these things, what is convolution with no example, I would not have got it. So you can also see this vector convolution is similar to polynomial multiplication. How? If a5 is something written as a0 plus a15 s plus an to sn minus 1, then if you multiply with cs, then you will got this particular thing. Uh, the polynomial of degree n plus m minus 2. So what it is? So if you try to find this coefficient c0, c1, c2, then it is somewhat similar to a0, b0, then a0, b1 plus a1, b0. So yeah, if you have seen this a0, b0, this is c0. Okay, this is c1. So this is similar to convolution also. CS. A vector into B vector. A vector convolution with B vector. There is difference between convolution and multiplication. This is convolution and this is multiplication. This is vector multiplication. Vector multiplication. This is convolution. Yeah. So this was only up to the examples. So this is, then again we will sir taught about the convolution is symmetric. So this A convolution B is equals to B convolution A. So have you ever wondered whether A B is equals to B A in matrix multiplication? So what we have observed in matrix multiplication, this is not equals. Okay. We will see today more about the system of linear equation that's coming in few, I think 10 or 20 minutes. Yeah. So matrix multiplication and system of linear equation, in that we have observed AB not equals to BA. But in convolution it is equal. So yeah, don't try to get confused. This is multiplication, this is not multiplication. Okay. Or also, convolution is associative. Either you change the order of the convolution, it doesn't matter. But yeah, this is similar to matrix associativity also. A, B, C. This is equals to A, B, C. Where A, B, C are matrices. Okay. Also, for a fixed vector A belongs to R power n, a linear function, this convolution is actually a linear function. So in previous classes, we have seen every linear function can be associated with a matrix. Okay, if we associate any function with respect to matrix, then it will be a linear function. So similarly, same thing is we are trying to do here. So what we are trying to do? We are writing convolution as a matrix multiplication. Okay, so what it is? For example, you have vector b as an input, and if you are multiplying with the t of a, t of a is a some matrix, then it is equal to a convolution b, and this is t of a is a special matrix which is called as Topliss matrix, and this is very special. It has a property, like if you can see, a1 is following this till a1, this one, then a2 is following this to a2. So this Topliss matrix is very important in applied linear algebra in AIML. Like whenever we see some layer, like a hidden layer or some layer, if we add in the neural network, then we try to multiply with the Topliss matrix. Also, if you have heard about CNN, convolution neural network, there also we use Topliss matrix. So just to introduce you what is Topliss matrix, sir is trying to write this convolution as a linear function. Now let's see this also. What in convolution, what we are trying to do? If we are having this vector of Rm, means this is B, okay, and then it is going to R of m plus n minus 1. So we had A as a vector which is in R power n, B as a vector which is in Rm. Finally, A convolution B we are getting as Rm plus n minus 1. Okay, this is what we are getting. Now, what if we try to associate with a linear function, then we are doing B multiplication with, this is multiplication with T of A. T of A is nothing but a matrix, or something you can write as a T. Okay, so B into T you are getting as A convolution of B. So T is made of A vector. You always remember, because B is already used. So T is made of A convolution B. Now let's see. This is T of A. This is not T of A. Okay, this is T of A. So yeah, this
Actually, this T of A is the weight and B is the bias in neural network.
uh no no,
Okay.
T of A is not way. Bias means you have to add. See, plus sign should be there. Weight, if you can really compare T of A with a weight, that is fine, because it is multiplying. Okay, but if you are comparing with a bias, then bias is just with this plus sign. That's why it is compared with a affine function. So T of A you can compare with the weights, yes, but by this B is not bias. Okay,
Okay.
yeah. So T of A, if you can see, A1, A2, AN. This will go to AN. Okay, and this will be M minus 1. Why M minus 1? Because you have to finally get output as M plus N minus 1. And this is M. So M rows. So you have to make sure this, if this is covering till AN, then you should have M minus 1 0, because this is M plus N minus 1. Okay, number of rows. So that's why this M plus N minus 1 cross M, okay, multiplied with M into 1. This is B. This is T of A. Finally, we'll get M plus N minus 1 cross 1. Okay. Yeah, you will get M plus N minus 1 cross 1, which is, this is a convolution vector. Suppose this is a convolution vector. We will get. So this is Topliss matrix. And we can say this convolution is a linear function. Okay. You always remember like how convolution can be written as a matrix form. This is very important. Okay. So sir also taught with one of the example. Suppose we have time series data x1, x2, xn. Then if a is some 1 by 3 factor, or it can be any alpha, beta, gamma. So what we are seeing, if you are getting T of A, okay, T of A you are getting multiplying this one. If this is B vector, let's see, this is B vector. So T of A is equals to this particular matrix into this vector. So this 1 by 3, 1 by 3, 1 by 3, then it should be associated zeros. So what we are trying to find is, we observed it, this particular, after particular time, this is giving you the moving average with window size of 3 for the time series data. So this, if you have seen 1 to x1 plus x2 plus x3, x will be 1 by 3 into 1 by 3, it will be moving average. Then x2 plus x3 plus x4 by 3. Similarly, it will cover all the data to xn. So after some point of time, with the after 2 order, it is giving moving average. So this is also one of the perspective, like we can see how the convolution is operating. So after some point of time, it is giving the moving average. It means that suppose you have time series data, this one, this one, this one, this one, then this one, this one. So this is actually the amplitude, and this is time. So this is sum to, convolution is sum to this one. Then convolution is sum to this one. After this, it is giving these three sum. Then these three sum. These three sum. So what it is showing? At some point of time, like it is time, it is increasing in time. And it is showing the average of it, the average values of it, this convolution. So it is required in some prediction of some time series data. I think you will not understand now because you don't know many concepts of yeah.
Ma'am, can you give me some real life examples of this time series analysis?
Yeah, sure. So suppose at time t is equals to 0, t is equals to 1, t is equals to 2, t is equals to 3, and suppose t is equals to n. So at every time, for example, weather forecast, you can say, okay, weather forecast, you can say, suppose weather is hot, sunny, okay, cold, and it is changing, okay, it is changing at every time. Now also, if you see, it's changing. If you want to predict the weather of Hyderabad, then it will be changing. So after some point of time, what we observe, this expected, what is expected? Suppose you are trying to give this as a reward of 0.5, 0.6, 0.7. That all these values will be probabilistic in nature, and that you'll give the values to it, all the weather conditions. Okay. At some point of time, you can't predict if the weather is changing very much, very it's fluctuating every time. Then what is the best estimate of it? Definitely the mean, right? If you are predicting 0.7, 0.8, 0.9. So this will be, if you are calculating the mean of this plus divided by 3, then it will be the estimate of it. Like you can say it is some mixture of sunny plus cold, like that. And also these data will be helpful in training a particular model. And if once this model is trained, then it will predict a new data will come. Suppose a new data will come. Any n plus n data will come. This is testing. This is training. Okay. Then it have to give the prediction. What is prediction? So it should be trained in this. So if it is fluctuating a lot, then you require to train a model on the basis of moving average. Moving means
Okay,
with a
ma'am.
time it is changing. Yeah.
Okay. Whether satellite navigation also comes in this category?
Satellite
Uh,
navigation. Yes.
okay,
Satellite
ma'am.
navigation also it is come.
Okay.
Uh, Amini, you are from which background?
Actually, I'm working as assistant professor in AI and data science.
Oh,
Okay.
AM,
AI,
AI data science. Where?
in Kerala,
Oh,
actually.
that's great. You are learning. Hmm.
Okay, ma'am.
Yeah.
Thank you, ma'am.
Yeah.
Thank you.
So till now we have seen vector multiplication and all. Now we will be going to matrix multiplication, trying to calculate the computation required. So this was the lecture, I think lecture 11, up to lecture 11. Now lecture 12. This matrix multiplication. So in first week I solved some of the problems. They asked us to calculate number of flops required, like number of additions and number of multiplications required in the matrix multiplication. At that time, I was not aware, and we were all the students were getting confused, like how the number of flops is 2 into m into n into p. So in today's class, we will see how the number of flops is changing. Why number of flops is required? Because it is changing the overall complexity of the system. And in linear algebra, everything is considered as a matrix or vector. So if we really see, we will see how number of computation is really affecting it. Suppose A belongs to m into n and B belongs to n into p. Then C is AB that belongs to m into p. So Cik is nothing but inner product plus sum. Okay. So inner product of the ith row of A with the kth column of B. This is actually okay. Now we know that inner product of ith row of the of the A and k column of the B is how much flops it requires. Can somebody tell me? So in first class we saw that it is 2n, order of 2n. Okay, it is actually 2n minus 1, but we say order of 2n. But since we are multiplying with the m into p, so total matrix, this is inner product. So total flops required for the matrix multiplication is order of 2n into, this is m, this is p, because m into p will be total number of flops. 2 into m into p. This is total number of computations required. Okay. So let's see graphically also. Suppose we are having I, k at entry. So this is ith row and this is kth column. So this is total, like it will be 2 into m. So the inner product of ith row with the kth column is n length vectors are there. Okay. So it will be n plus n. Okay. So 2n. I hope you understood. Okay. Now we are calculating MP number of inner products because M is the number of rows of A, where P is the number of columns of B for matrix multiplication. So MP will be multiplied. So number of flops in matrix multiplication is 2 into M into P. Now we will see some of the cases. Suppose inner product is there, simple inner product, n length vector. So this is n equal to 10. Matrix multiplication. Here P is equals to 1, right? So m and 2 into m into p. Because matrix and vector, only one column will be there. So 2 into m into p. Here 20, because 2n. If m equals to n equals to p. So if matrix multiplication is required, then 2 into n cube. So have you seen that? It is growing exponentially here. So the order of multiplication is very important here. So if we see some of the composition function, let's say you are having r of n1 and then r of n2. So here we are directly jumping to jump from this matrix vector multiplication to composition of the linear functions. Okay. And always remember, linear function is nothing but it is associated with a matrix. Okay. It is always associated with the matrix. Okay. So yeah, what I was saying, huh? So if T1 is a function from n1 to r of n2, and T2 is another function from r of n3, so can you directly write the association between r of n3 to r of n1? So this is called the composition of functions. So composition only exists for a linear function. You always remember. So if x is converting to t1 of x, and then t1 of x is converting to t2 of t1 of x, because this is again a domain. This is domain of t2, and this is range of t2. This is domain of t1. Okay. So what we can write? This is T2 composition of T1. It can be written like this. And it can be written as T2 into T1 of x. So what we have seen in the previous classes, T1 and T2 can be written as a matrix. Okay. So since it is a linear function, let there exist A1 belongs to R of N2 to N1 be a matrix of T1, then T1 can be written as A1 of x. And since T2 is also a linear function, then there exists a matrix of A2 from R of N3 to N2 of T2. Then what we have seen, then what we are trying to see, T2 of T1 of x, which is nothing but T2 composition of T1, is nothing but A2A1 into x. So this A2A1 is a matrix representation of T2 composition of T1. So composition of linear function is also a linear function. We are trying to say this. These statements are very important. Okay. Yeah. So composition, what now we have seen the till linear function. Let's see what is composition of affine function. So affine function will be associated with the bias. Okay. Then T2 will also be associated with the bias. T1 will also be associated with the bias. Then we are trying to find T2 composition of T1. Then what we are seeing, in fact, T2 composition of T1 is also a affine. Affine means what? There should be something bias and there should be some matrix associated with the x. So this is A2A1 is x and this bias is A2B1 plus B2. So composition of affine function is again an affine function. Now we will see some of the properties. So function is associative composition. This implies matrix multiplication is also associative. As in the initial 5 minutes, I told that matrix multiplication is associative but not commutative. Okay, so how it comes from? So this is the reason. Since the function is associative function, this implies matrix multiplication is also associative. So if A, B, C, okay, are some vector from some matrix where belongs to P, Q, and then QR, then RT, then order doesn't matter. But yeah, always remember AB not equals to BA. Okay. Now we will see some examples. If A is wide vector, B is also some column vector, then this ABC also holds in vector also. But if you see in matrix, it also holds. Now we will see some of the example that is showing the computation complexity. Suppose you have this A as a wide vector and this B is a wide vector. Now if you calculate from BC to A, so it is showing the complexity of 2 of n square. Okay. Now if you try to get AB first, then C, then it is showing the complexity of n, order of n. So it really matters, like which order you picked up. Just don't go through, just don't jump into the matrix multiplication. Otherwise, it will be very difficult for you to compute the whole things. In fact, in Python or MATLAB, this is followed inbuilt. Like they are following inbuilt. The software itself follows. So you don't have to worry about it. But yeah, if you're calculating by hand, then the order also matters a lot. Because first A, B, C, it is giving a n cross n matrix. Okay. Then again, it will be multiplied by a matrix. Whereas this is giving you only a scalar. And then it is multiplied by one vector. So that's why it is order of n. And this 100 square and 100 is very, very different if the order is very high. So yeah. So this is taken care in terms of programming also when we do. So what we have seen in this lecture, composition of linear and affine function is affine and linear, matrix multiplication also, and associativity of matrix multiplication. So till this lecture, I think lecture 30. Then we will see some of the system of linear equation and their solutions. So from here, this is very important. In fact, forms the basis for everything, like robotics or everything. How is there anyone? Okay, let me see the chat box. Air conditioner demand. When did you tell this thing?
At time of time series data analysis.
Okay. Okay, so if you have any doubt, you just unmute yourself and tell. I'm not checking the chat box very frequently. So yeah, moving to the system of linear equation, and we have to check whether the solution exists or not. So one thing I'd like to you to just think how the system of linear equation looks like, and why we are calculating the solution. So don't try to directly jump to the equations and then some formulas and then some ratta things. Okay, so try to analyze it by plotting or something like that. So actually every equation is nothing but it's a line or hyperplane, you can say. So if you try to draw 2 3 lines, suppose this is one line, this is one line, this is one line. Okay, I'll draw. This is one line, this is one line, this is one line. So you can see 1 2 3. These every lines will have the one equation, equations. Now if we have to check whether these lines are crossing or not. So if these are crossing, then this shows a solution exists. Suppose these lines are not crossing, then it shows no solution exists. And suppose all lines are very parallel to each other, then it will be infinitely many solutions. So this is the actual significance of solving a system of linear equation. Okay, suppose a matrix A belongs to M cross N. To compute X, which belongs to R power N, then such that AX is equals to B, then what you have to find? You have to find X. Okay, so AX is equals to G is given, B is also given, you have to find X. There will be M equation and N unknown. We will see with examples. Okay, so for example, A is 2 cross 2, B is 2 cross 1. Then there are two equations. This matrix multiplication itself is following the two equations because matrix multiplication is nothing but a linear function. So this is row interpretation. You are actually solving row. Okay, and we are getting two equations. Now let's see if you are solving with respect to column. This is C1, this is C2. How you can write? So if you can write this one, you can write C1x plus C2x x1 C2 is equals to B vector. What is C1 C2? C1 is A11 A21, C2 is A12 A22. Okay, so these things are row interpretation, and this thing which I write in red color, this is column interpretation. We will go more into it, then only we will understand left inverse and right inverse by seeing the column interpretation. So just for your glance, this is column interpretation. I am keeping one column as one of the vector.
Ma'am, where actually this column interpretation is used. When we solve that equation, we actually use row interpretation.
Yeah, column interpretation is used. Just give me 5 minutes. We will go deep into it, very deep.
Okay.
Yeah. So this is column interpretation. What if you see this particular thing? So if you see x1 and x2, okay, x1 and x2 are unknowns, and c1 and c2 are the column vectors. This is nothing but vectors. So if you see c1 and c2, c1x1 plus c2x2, this is nothing but the linear combination of columns. If you vary x1, x2 to many ranges. Now we will see more into it. So yeah, this ax is equals to b. So if A is written as a1, a2 to an, where a1, a2, an are the column vectors of matrix A, where we have seen c1, c2 like that. Okay, then ax is nothing but a1, x1 plus a2, x2 plus an, x1. So if we see x as a linear combination of the columns of A, so what it is, this is nothing but linear combination. You always remember this one. Linear combination of columns of A. Okay, where if you remember our definition for linear independence, what we saw, if any vectors, suppose v1, v2, vn vectors were given, then alpha, there exist a scalars alpha, beta, gamma to some gamma n. Then what we saw, alpha v1 plus beta v2 so on plus gamma n vn is equals to 0 if and only if alpha equals to beta is equals to gamma n is equals to 0. So this was the condition for linearly independent vectors. Okay. Now, then after that we saw what is a linear combination of the columns of A. So this alpha v1 plus beta v2, these will be called as a linear combination of columns of A. Similarly, in this sense also we are trying to get is a linear combination of columns of A. Now what is this? Let's see. Given B and A, B is already given, A is already given, you are trying to find X. This is unknowns. Okay. Then if B is a span, B belongs to span of this thing, if, which is nothing but the column space or range space, then what we call, if this condition is followed, okay, then we say solution exists. Or in some books it is written as consistent. Okay. This means it exists. So what is the condition? First of all, we are trying to extract the columns of a vector of a matrix, which is a1, a2, an. Then we are trying to get, this is column space, and we also saw this column space is nothing but a subspace. If anyone don't remember any concept from the previous class, just let me know. I'll again explain here. But yeah, don't get confused. This is also we saw in previous classes. This is subspace, which we also called as a range space. Subspace belongs to R power of n. Okay. So if B belongs to span of this thing, then it is then solution exists. Let's see graphically. Suppose column space of A is this one. This pink green color is column space of A, and B is a vector inside lying in a column space of A. This means that there exists a solution which is nothing but a linear combination of the columns of A such that Ax is equals to B. So this condition is solution exists.
Ma'am, actually, what is meant by span?
Yeah, span is nothing but a space taken by columns of a set of vectors. For example, you have two vectors, 1, 2 and 2, 3. Okay, this should be linearly independent. Okay, span is only calculated by linearly independent vectors 2, 3. Okay, now these are vectors. Okay, v1, v2. Now you have R2 space. R2 means two dimensional, x and y. Now let's see v1 alpha v1 plus beta v2. Now you vary alpha and beta from minus infinity to infinity. Okay, suppose alpha beta is equals to 1, this particular value is coming, this particular vector is coming. Okay, let's see v1 vector, this is v dash 1 vector. Okay, then alpha beta value is equals to 2, 3, then again v2 dash vector will come. Then similarly infinite number of vectors will come, right, such that it satisfy alpha v1 plus beta v2. Then there will be so many vectors. Okay, so this will create a plane. Okay, suppose it is passing through origin, so it will create a plane. This particular thing is called span of vector v1 and v2. Span of vector v1 and v2. This is called span. And you always remember span is created by linearly independent vectors. So if v1, v2 are linearly independent, their linear combination means alpha v1 plus beta v2 is linear combination of vectors v1 and v2. So linear combination of vectors creates a subspace in R2. So this is called span.
Okay, ma'am.
And this span, and similarly if we relate here, this thing to here, this is created by, this green color is created by linear combination of column space of A. Okay, this is linear combination of column space of A. This is span of. And if we say the B vector, which is the output vector, that we are getting Ax is equals to B, this is creating some span. This is green color is span. If B vector is in span of this vector, Okay, then we are saying there exists a solution. Otherwise, it doesn't exist. Okay, and solution will also be some linear combination of columns of A. Also, there exists a solution X such that this X is a linear combination of columns of A. So here the column interpretation is very important. So here it is used. So what we are trying to do, we are just splitting the matrix into columns. Then we are trying to get a span where linear combination of columns of a matrix. Then we are checking whether this B vector is lying in the column space or not. If it is not lying, then we say that the solution doesn't exist. We are not telling about anything about unique solution, infinite many solution or anything else. We will go into it in the future in 5-10 minutes. Okay, I hope this is clear. So what the next thing is, if B vector is lying outside of the span column space of A, then there is no linear combination of columns of A can get B. Okay, this is no linear combination of columns of A can get B. So this means there doesn't exist a solution to Ax is equals to B. No solution. Okay, yeah, I think up to this point this is clear to everyone. So if you have any doubt, I'm waiting for just a 1 minute. You just ping me in the chat box. I'll let you know. So I hope there is no question. So moving ahead. So what we have seen, Ax is equals to B. Again, we are starting with Ax is equals to B. Given A belongs to M cross N, B belongs to R power N. Then find X such that Ax is equals to B. Recall, if range of A is a column space of A is a subspace. I hope you remember subspace. Then there exists a linearly independent space. In subspace, what we saw that there will be a linearly independent sets. Linearly independent sets will only create a subspace. And similarly for the span also. There will be existing similarly in a different form it is written. There will exist a linear independent set. Then range of A will be simply the span of V1, 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 V2, Vr. Similarly, if you are trying to find the range of A or dimension of the subspace of A, this is nothing but the rank of A. So rank is nothing but the dimension of the subspace created by the columns of the matrix A or any matrix. So also this is augmented rule. If you see, rank of A is nothing but the rank of A of B. Why? Because B is the linear combination of the columns of A. Definitely it will be same. So if B belongs to span of A1 to AN, this implies B is a linear combination of columns of A, and also Ax is equals to B is equals to solvable. So what is this? Again, we are trying to interpret it as, if columns of A are linear independent, these columns are the basis vectors of a range A. So in the previous classes also we saw linear independent implies basis vectors. Basis vectors means what is meaning of basis vector? Basis vectors are nothing, the vectors which are linear independent, and from that vector, any vector in that span can be created by the linear combination of those basis vectors. Okay, so since B belongs to a range of A, B can be uniquely written as a linear combination of columns of A. Then Ax is equals to B has a unique solution. Okay, now I think this is not clear to you. So what we saw, if we have A, okay, A is a matrix. Then we are trying to write A1, A2 to AN. Okay, now we are trying to create a span by A1, A2 to AN. Okay, span is nothing but a linear combination of these vectors. Okay, now we saw if B belongs to this particular span, then there is a solution exists. Now on top of it, if solution exists, then we are trying to tell whether there is a unique. There can be many solutions and can be unique, right? Whether there is a unique solution or not. Then we saw rank of A is equals to rank of A augmented with B, because B is lying into this, and then definitely B is some dependent on this. Okay, so if dependency comes, then definitely this rank is equal. Now we are telling whether if rank of A is equals to dimension, means n. Okay, n means number of columns. Okay, means linearly independent. Okay, yeah, I think my system went to sleep, so it got cut off. Yeah, so what I was telling, if solution exists, then whether the question is whether there is a unique solution or not. So what we are trying to get rank of a matrix. If the rank of matrix is the dimension of the matrix, then it means this is linearly independent. So if the linearly independent
There's
columns
no
exist,
audio.
oh so sorry, yeah, I was trying to tell, but yeah, so it was muted. So sorry, I'm again repeating. If solution is existing, then what we are trying to find, whether there is a unique solution or not. So we saw rank of A is nothing but is equals to rank of A augmented with B. Now, if we try to find the rank of matrix A, which is equals to dimension of the matrix, which means this is linearly independent, then we say that solution is unique. So yes, again repeating, this is all about solvable things. Then if these particular columns are linearly independent, then solution is unique. Okay, so first we saw whether there is solution existing or not, and if it is existing criteria was B should belongs to span of A1 to AN. Okay, and if B is linearly independent, the solution is unique. Okay, this is all about, we will see with some of the examples also. So if you don't get some of the points, don't worry, we will again see. But yeah, system of linear equation is very, very important in every aspect. So try to understand it. Okay, and here the column interpretation is very, very important. Now, sir gave some polynomial interpretation. If you are having some polynomial q of s is equals to q0 plus q1s to qn minus 1 s power n minus 1. So, if we have objective, suppose this is the number of points xi, yi. So, you have to compute this particular coefficients. So, how you can compute using system of linear equation? How you can write? Sir gave. Okay. So, you can write like this. If you are having this one, this is a vector 1 ai, because everything is multiplied with these coefficients. So 1 xi square xi n minus 1. So it can be written in the form of ax is equals to b. Now you are trying to find this particular coefficients. This is x. Okay. This is what? This is x. So this can also be solved using system of linear equation. One of the basic example of solving system of linear equation, finding the coefficients of a polynomial. Because polynomial, every time you are trying to fit a data set. So in practice, what it is? This is a data set. This is D data set x1 y1 x2 y2 x3 y3. Then this is one of the non-linear composition. You are trying to make it as a non-linear composition. Now at the end, for the prediction, you will require this q0, q1 to kn minus 1. So how will you find? Using system of linear equation. I hope this is clear. This was one of the example. Now ax is equals to b, where a belongs to r power m cross n, b belongs to r power n. Now if you are having, we are trying to find now left inverse. Then we will see right inverse. Then we will see what is inverse of a matrix. Actual practical application. Inverse of a matrix. Just give me a minute. I will just plug the charger. My laptop is running out of it. Okay. So let's see with one of the example. If this matrix A is simply a scalar, okay, suppose alpha, only component is alpha, beta. Then if you are trying to find A alpha x is equals to B, then what you do? X is what? Simple 1 by alpha into B. This is multiplicative inverse, we can say. But this x is a solution also. I hope you all agree, provided alpha not equals to B, 0. But is this also follows in matrix? We will see. So suppose Ax is equals to B, we are just having this particular solution, system of linear equation. Then in order to find x, we can write this A inverse of B. Are you agreeing of that? I think agree. Okay. Now, we have to first check whether this inverse exists or not. Because many times matrix inverse doesn't exist. Okay. Means it's not like a simple scalar. You can just 1 by alpha you will do and you will get this inverse of a matrix. So for that checking only, we are trying to find left inverse and then we will go to right inverse. So this is one of the basics of everything. What is left inverse of A? So given a matrix belongs to Rn cross n, a B matrix, which is an inverse matrix, is known as left inverse of A provided B of A is equals to I. How will you remember? Left means left of A. Okay, this B is left of A. Suppose if I write A of B is equals to I, then this will be right inverse instead of right inverse. Okay, this is right. So sir is representing right inverse by C, right, and by B, left. Okay, you also follow this. So what will be the size of B? Similarly, it will be size of same as A transpose. I hope you all agree, because then only this will give the I of M into N. Sorry, I is always a square matrix, N cross M. So the size will be N into M, because A size is M into N. So identity matrix is always a square matrix. Don't try to get confused. Okay. So if A is left invertible, now we have to check for what type of matrices the left inverse exists, because in many cases left inverse doesn't exist. Okay. Example, let A belongs to R1 So if A is not equals to 0, then 1 by A is generally a left inverse. If it is basically a scalar, as we have seen in alpha beta case also. Okay. So if A is a vector, then there also exists a 1 AJ not equal to 0, where B is equals to 1 upon 8. Let's not say with AJ and all. Let's see with one of the example. Okay. Suppose you have a tall matrix. Tall matrix means you have number of rows greater than number of columns. So in every tall matrix, okay, there will be many left inverses. Let's see one of the example. Suppose B1 is this thing, 1 0 0 minus 1 0 0. This B2 is 0 0 1 minus 1 1 0. Okay, so if you are trying to multiply with a B1A is equals to I2, and also B2A is also I2. So here we have seen if B1 B2 are left inverses, the every linear combination of this B1 B2 is also a left inverse. So what we have seen for a tall matrix, you are getting how many left inverses? Infinite left inverses. Because if we say linear combination, this alpha can be anything, right? So this is also a left inverse of A. So always remember left inverse exists for a tall matrix. Now we will see why left inverse doesn't exist for a wide matrix. Okay. Left invertibility of matrix and linear independence columns of A. Suppose these columns are not linearly independent. If it is not linearly independent, then definitely we will have so many left inverses. Suppose if A is left invertible, and there exists if it is left invertible, then there exists a left inverse B such that BA is equals to I. To show that these columns are linearly independent. Okay. So if it is left invertible, then what we are claiming, the columns of A will be linearly independent. So let's see Ax is equal to 0. This should implies x is equal to 0. Why? Because we have seen uh, what is the condition for linear independence? We have seen alpha v1 plus beta v2 plus gamma v3 is equal to 0 if and only if alpha is equal to beta is equal to gamma equals to 0. Hope you agree. This was a condition for linear independence. Similarly, we saw this Ax is nothing but the x1 a1 plus x2 a2 plus xn an. This is nothing but a linear combination of the columns of A. Columns of A. So we saw if we are putting as a 0, then we have to show for linear independent x1 equals to x2 is equals to xn is equals to 0 from the condition of linear independence. Now we are showing whether this is equals to 0 or not to show whether the columns of A are linearly independent or not. So let's see if you write 0 is equals to B into 0. Okay. And B is nothing but the left inverse. Okay. So B into AX. Now you can write BA into A. Since this is nothing but I. So it is equal X. So what we are trying to get? X is equal to 0. So this is proved. Sometimes if you don't get some of the proofs, just leave it. But try to get the actual statement at what it is showing. So columns of A are linear independent. So what we observe, if A is left invertible, then columns of A will be linearly independent. Okay. Where it is used, we will see. It is used in pseudo inverse calculation and linear regression, and everywhere it is used. Now we will see. We have seen the property of left invertible. Now suppose A is left invertible. Let's see this one. This particular thing. Then independence dimension inequality states that n should be less than or equals to m. Means this particular thing, left invertible should be only applicable to either tall matrix or square matrix. What does this mean? Tall means m is greater than n. Square means m equals to n. This is what it is showing. Why matrices we cannot calculate left invertible? Just now we saw that left invertible will only be applicable for linear independent columns. So have you ever observed, have you ever wondered, like for wide matrices, the columns of the wide matrices will be linearly independent or not? It will not. Okay. So what we have seen, in fact, in every case, wide matrices, the columns of the wide matrices are not linearly independent. So that's why we cannot calculate the left inverse of wide matrix. Okay. Why it is? Because in wide matrix, m is less than n. Okay. So definitely there will be some column which are the linear combination of other columns. Okay. So that's why we cannot calculate left inverse of wide matrix. So for wide matrix, we calculate right inverse. Okay. And when right inverse is equals to left inverse, then that will be a square matrix. And that is a common inverse, that will be simply the inverse of the matrix. Okay. So we will see right inverse just in upcoming 5 minutes. Okay. So wide matrix, number of rows strictly less than number of columns. It will not have left inverse because columns of A for a wide matrix are linearly dependent. Because just now we saw if it left inverse exists. Ma'am, which textbook are you following for problem solving? I'm not following any particular textbook, but I love this Bishop book for PRML, which is pattern recognition and machine learning. And for linear algebra also, Gilbert Strang, I'm just typing. And then
Ma'am, actually in assignment 1, I think some answers are given as wrong.
okay. Yeah, just you report it. How to report, you know?
Yes, ma'am. In feedback, I already reported in feedback section.
Yeah, it will be corrected. No worries.
Okay,
It will
ma'am.
be corrected.
So got
Uh,
confused by seeing that answers actually.
yeah. In fact, in last year also, like I will just go through some of the problems. It is very important to connect with the theory with the problem. So I will definitely go through the problems. So in that last year questions also,
Okay, ma'am.
I saw
Who
some
is
of the,
actually
yeah.
who is
Tell me,
actually
who is?
updating that answers? Who is actually updating that answers in the assignment section?
Yeah. So basically, we are just external PMRF students that we are asked to give the only live sessions and solve some of the problems related to it. But this particular NPTEL assignments that will be taken care by IIT Kharagpur TAs only. IIT Kharagpur NPTEL TAs.
Okay.
So if you since you have informed me, I will
Okay.
anyway inform them. So no worries.
Hmm. Okay. In
Yeah.
question
So
number
have you ever
in
report
assignment.
like you should report it properly, otherwise it will not be corrected.
Actually, in maths, that is very difficult when the answers are given wrong.
Yeah, I agree.
Okay, ma'am.
Like in the answers also, did you find the detailed solution or something?
Yes, ma'am. In detailed solution, actually, I verified, but the answers are some answers are actually given as wrong.
Okay. I will inform them, so don't worry, it
Mm.
will be corrected.
Okay, ma'am. Okay, ma'am. Thank you.
Yeah, yeah. So Sampath Kumar, you can just check with the Gilbert Strang textbook. It's very good. Like he's a mighty professor who teaches applied this linear algebra, and the some set of problems are there. Apart from this, if you are really interested in AIML part, then Bishop PRML book is there. Okay, and just one suggestion. Yeah. So yeah. So what happens whenever we try to do this linear algebra, we often get confused with some of the concepts. So don't try to miss anything. Like don't try to just jump into. Suppose you are reading week 3 now, and you have read that week 1 a very long back. And what we do generally is, if we have read something, then we don't revise. So okay, even I also don't like to revise. Whenever we read, we don't like to revise. But if you don't revise and correlate the things with the previous things, then definitely it will be very difficult for you to cope up. This is only up to week 3. The things will get tougher by week 8, I think. Yeah, week 8 and week 9. I have seen the course structure. Like it will be Markov chain, then some of the properties of the algorithms and all. We will see all these things. So if you don't remember the previous things and don't try and you're not able to correlate with the previous things, then definitely you will drop the course or either won't continue the course. So I've seen many people drop the course after week 4 or week 5. So that's why I asked how many of you watch the lectures. Even if you're not watching the lectures, fine, because anyway I'm going through the first the theory things and then I'm going through the solutions. But yeah, if you are having some time, you can watch the lectures. Just keep it in front of you, take the notes. Anyway, sir has posted his own written notes. So you don't have to create your own notes. So it will be very easy for you to just go through it. Yeah, okay.
Ma'am,
So this
can
was a
we get
little
more problem solving sessions? Because it's a
uh
bit confusing for a person like me who has not much concepts of linear algebra.
okay. Radhika, have you seen week 1, week 2 lectures?
Yeah, ma'am.
Okay. Uh, have you joined my first week live session?
No, I didn't attend that session, ma'am.
Okay.
Will it be available in recorded videos?
Yeah, it is available. Please
Okay,
go through it.
okay.
Yeah, so what it is like, if you miss something, like today also I'm just relating with the subspace, linear independence, everything. I'm just assuming that you have went through that and then only you will be able to correlate. So yeah, Radhika, just a small suggestion.
Hmm.
If you are not able to watch all the lectures and all, but problem solving section, if you are attending every week, then
Okay.
it will be very useful for you to solve the problem. We will see how to solve the problem also in just 10 minutes because this is about to finish.
Okay.
So don't worry about the problem sessions because anyway you are having in 1 week you are having 2 sessions, that too of 2 hours.
Okay.
Okay. Other person also taking, I don't know the class timing of that person. Can anyone tell me like what is the class timing of other TA so for problem solving?
And we are only seeing only one session.
Really? He's also taking classes. I will tell you. Wait. He's also taking classes. So his name is PM Sai Krishna. I don't know his, I don't remember his timing. Someone texted yesterday 7 to 9. So yeah, every Friday he's taking from 7 to 9. Okay. And I am every Saturday I'm taking 6 to 8. So we are having 2 live sessions, that too live, like you can contact directly, you can speak, you can unmute, you can ask questions. So 2 live sessions from all of you please remember this is Friday from 7 to 9 and then Saturday mine is 6 to 8. Okay, Radhika, you try to attend these lectures. Even if you are not able to attend, try to watch my previous live sessions. It will be helpful. Like it is uploaded in the YouTube. I just share my link, the chat box. So see, I'm still wonder like many of you people don't know about the sessions that taken by us, and we wonder why people are not joining in our class because we have to give our attendance. So yeah. So fine. So we saw this left inverse is not existing for wide matrix. Why? Reason you know. Okay. Okay. And also from the theorem, we saw this left invertibility implying is linearly independence of the columns. Okay. So linear independence of the column is this is vice versa. It implies A is not left invertible. Now, using left inverse for solving Ax is equals to B, assume that suppose we have Ax is equals to B has a solution. So if B exists, left inverse of B, provided columns of A should be linearly independent. Then what it is? If suppose Ax is equal to B doesn't have solution. So let B be a left inverse of A. So what I'm trying to tell, I will again explain. Suppose there exists a B. B means left inverse of A. So if B exists, okay, now we have to check whether a solution exists or not. There can be two criteria. Okay, either unique solution or no solution. Okay, whereas this is not the case for right inverse. So I will again relate in that. So if you calculate BB, this BB is nothing but B into A of X because Ax is equals to B we saw. Okay, putting B as Ax, then if it is equals to X, okay, then it is a solution. So suppose this X, suppose X is BB. Now you put Ax as A into BB. Now A B into B. Okay. Now, if it is equals to B, then solution exists. If A X is equals to A into BB. Why BB? Why BB? X is equals to Y BB because according to left inverse, this is okay. Okay, if it is not equals to B, then solution doesn't exist. Since the same analogy that it will not in the span of columns of A, then this implies the solution doesn't exist. So from the left inverse also we are trying to get whether the solution exists or not. First of all, we will see whether there is existence of left inverse. What are the conditions for left inverse existence? The condition for the left inverse existence either for tall matrix or linearly independent columns of A, Okay, then we will calculate the linear independent columns of A, whether it is linear independent or not. Then we will see whether the left inverse exists or not. Then definitely the left inverse exists. Then if AX is equals to B, you will calculate AX is equals to B. If AX, where A into BB is equals to B. If it is equals to B, then solution exists. If it is not equals to B, then solution doesn't exist. So this is the criteria for calculating whether the system of linear equation has a solution or not. Okay, why BB is X? From the left inverse property. BA, which is I. BA is nothing but I from the left inverse property. This is X. Okay. Now, again, same is written. Given a system of linear equation, AX is equals to B. If let A be a left inverse and B is a left inverse of left A is a left invertible and B is a left inverse of A. Left invertible means all the columns of A should be linearly independent. Then you have to check if BB satisfies the system of linear equation or not. If it is not, okay. If yes, solution. If not, no solution. So what are the conclusion of this lecture? A is left invertible. It implies columns of A are linearly independent. Also, range of A is column spans of A has the columns of A as its basis vectors. Okay, if the linearly independent exists, then this will also be a basis vectors. Only if this is existing, and it is solvable if it is belongs to range of A. If left inverse invertible, then B can be uniquely represented as a column space of A. This implies uniquely present because we have seen this particular thing. This is B is inside that span. There exists a unique solution. For any left inverse of A, if it is solvable, there is the solution. This is all about left inverse. Okay. This is all about left inverse. So left inverse of matrices may have left inverse. Okay. This is square. This is tall. It never have left inverse. This is wide. Why? Because these are linearly dependent columns. How to use left inverse to compute the solution of A? By checking with these conditions. Checking these conditions. Okay. Now we will go to right inverse. This is the last part. Then we will solve some problems. Actually, it got delayed. This content was too much. Yeah. This was the last theory part. Then we will solve the problems. So don't worry about it. So yeah, if it is A, this is a right invertible matrix. If there exists a matrix B such that AB is equals to I. Why it is B? It is written here because it is a right part. Okay. AB is equals to I. Okay. Let's see. Let's calculate the transpose of A. Transpose of any square matrix is square. Okay. This is B transpose, A transpose. So what it is? This B transpose is left inverse of A transpose. Are you able to relate with that previous one? Because we saw BA is equals to I, then we were telling B is a left inverse of A. Similarly, B is a left inverse of A transpose. A transpose is a left inverse of A transpose. Similar analogy we are following here. If we say B is a right inverse, then B transpose is left inverse of A transpose. Okay. B transpose is left inverse of A transpose. You can relate, you can just convert B into C anyway, but any other matrix also you can take, but that doesn't matter, but this should follow. Okay, so if A is left invertible, this implies columns of A are linearly independent. If we transpose it, let's keep it a transpose, then A will be right invertible. Then it means rows of A should be linearly independent. I hope you got it. Now, why right inverse exists only for wide matrix or a square matrix? So, if rows of A are linearly independent, this means our matrix is not right invertible. So, what we saw earlier, if columns of A are linearly independent, then the matrix was not left invertible. Similarly, if row of A are linearly independent, the matrix is not right invertible. So, tall matrix will never have right inverse because rows are linearly independent in tall matrix. Now, using left inverse, we saw there was two conditions. Okay, either system of equation is giving a solution or not. Okay, but this is very interesting. In right inverse, you always get a solution. Okay, how? Let's see. If Ax is equals to B, to solve this, given A is right invertible, there exists AC is equals to I. C is a right inverse of A. Then let's keep x is equals to CB. Why x is equals to CB? Because AX is equals to B. Then x is equals to A inverse B. CB. Okay. This is solution, right? So if AX is equals to B, if you solve AX is equals to A into CB, if you keep, this is AC into B, and this is always I. So this is always giving AX is equals to B. While in left inverse, AX is equals to A into BB. Okay. This was AB into B. Okay. Now we have to check because BA is equals to I. Not always guarantees this, all doesn't mean always that AB is equals to I. There will be some cases where AB is equals to I also, but yeah, we have to check whether this is I or not. This is B or not. So this was a case for left inverse. But in right inverse, this is always B. So if it is light invertible, then there will always solution. So have you seen in the white matrix you will have infinitely many solutions because you will have less number of unknowns and more equations. Okay. So inverse of a matrix. So if any matrix A is left as well as right invertible, then we say that A is an invertible matrix. So means if it is equal, a left and right, so it will be square matrix. So same thing. And if it is square matrix and single inverse will be existing. Okay. So yeah, similarly same analogy is there. I think we can leave these things. This is just simple analogy for square matrix. Square matrices are very simple. You can definitely get some analogy of square matrix. This is the last lecture of something, I think 30 minutes only I left it. So in that 30 minutes, last 30 minutes, this was the right invertibility is checked, then invertible matrix is checked, then pseudo inverse of A is also checked. So if you want to see pseudo inverse is nothing but if the columns of A are linear independent, the pseudo inverse is calculated A transpose A into A whole inverse into A transpose. So yeah, this is very important to remember. And this is also called as a left inverse. So in future lectures also you will be asked to calculate right inverse. So I remember that right inverse A transpose into A transpose the whole inverse. So you have to remember these equations because you have to anyway calculate it. So yeah, we will go to the questions because anyway we are running out of the time. I just want to cover the questions. If you have any doubt in the last 30 minutes of the lecture, so I think if I remember, it is lecture 15. Lecture 15 is the easiest one. Up to lecture 14.5, like 15 half part I have covered. But if lecture half part you want to, last half part you want to again discuss, and we will discuss in the next class because I just want to discuss the questions. So similar type of questions will be there in the week 3 assignment. So let's see. Consider function fx is equals to 5 minus x square power 1 by 2. You have to calculate f of fx. Composition of the function. Try to calculate. I just want my session to be very, very interactive. How will you calculate? This is very, very simple. So hint is also here. O is a composition of functions. You just have to calculate f of, tell me the answer, f of fx. Yeah, giving you 2 minutes, just tell me the answer. Viveka is telling 1. Guru Swami is telling D. I'm waiting for Heeraj. I'm waiting for Radhika, Ambili, Vijay Kumar, Lakshmi, Sampat Kumar, Pradhan. So since you have your colleagues have solved, you can also solve. This is the assignment of last year. So similar type of questions are only framed in this year also. Nice. So 3 people have told x. So you only have to calculate 5 minus x square 1 by 2 1 by 2. This is square. 5 minus 5 minus x square 1 by 2. Okay, this is 5. This will be sum plus 1 square by 1 by 2. This is x. Okay, very nice. So those who have answered 1. Anyway, those who have tried also, for them also it's very nice. Okay, so let's solve this problem. So let A is Rn. This is square matrices. Which of the following is what? True. Whenever this type of question comes now, so if you are getting some doubt, so you can take the example of any 2 cross 2 matrix and just check. Okay, Sampat is telling C. Ambili was also telling C. Anyone else? Okay, so everyone is telling C, so it's very correct. In fact, the inverse as well as transpose also, if you are asked to calculate transpose also. So this is also B transpose A transpose. Okay, just now we saw. Okay, so answer is C. Now, identify for which of the following matrices left inverse exists. So what are the properties of left inverse? What are the properties of left inverse?
Columns are linearly independent.
Yeah, very, very good. Yeah. So yeah, try to find this. So your colleague has told the hint. What should be the answer? A cannot be the answer. It's a wide matrix. So you are having option B, C or D. You have to check. Viveka is telling B. Anyway, take 1 minute time. Anyway, you cannot just jump. So your colleague has told B. Very good. He is telling B. Okay. So I think it is very clear. You can just check with the linear independence property, which is vector 1. You have to take 1 0 1. Then vector 2 as 0 1 0. Then alpha v1 plus beta v2 is equals to 0. It should imply that alpha is equals to 0 and beta is equals to 0. So I think B is the answer. So yeah, you all are correct. Very good. So moving to the next question. So some theoretical understanding is there. Okay. So, so I'm reading out the question. Which of the following statements is or are true? So you can have one option as well as 1, 2 option. So if X is a left inverse of A, then X is unique. Okay, first is this. Then if X is a left inverse of A, then columns of A are linearly independent. Then third is if A belongs to R power M cross N, then if N greater than M, this is what? No, this is wide matrix. Then there exists a left inverse of A. And if X be a left inverse, Y be a left inverse, then X equals to Y. This is very good question. I just want answer from all of you. So Guru Swami has told D. Then Ambili is also telling D. Okay. Waiting for Radhika, Vijay Kumar, Lakshmi, Mani, Heeraj, Vivek. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I just don't want in the next class 9. So this class 9 people have joined. The next class also please join all of you. Okay. So everyone is telling D. So let's see D option. So since first option is very wrong, we just saw with the example also. It's very wrong. Yeah, WhatsApp group for discussion. I will also join that group. So in that discussion, yeah, you can check with the answers also. But yeah, if you are able to solve by yourself, it will be very helpful for you only. So it should be a discussion of concepts, not the answers of the assignments. I just appreciate that. Okay. Anyway, you can discuss anything. It's your thing. But yeah. Yes. So option B is then we just saw it should be same, and then the third one is definitely a wrong because it is wide matrix, and fourth one we just saw it's square matrix. It will be same. So yes, till this point everything is clear to all of you. Okay. So moving ahead. Now solve this. Let A is equal to this thing and V is some x such that Ax is equal to 0 means it's a solution. V is a vector of solution. The dimension of V should be you have to calculate rank. Okay. Is anyone checking linear independence thing? Like how we are following? Guru Swami, can you tell me your logic? Acha, Ambili, tell me your logic. Number of linearly independent vectors.
Actually, this one rank of A equals
Rank of A
dimension of
is
A
equal
equals
to
dimension of V.
yeah. Yes.
Okay.
Anyone else who want to try? So answer is C. Anyone told rank is 1? Yes. So Viveka is very true. So since rank is 1, okay, this x, the value should be how many values are existing. So you have to calculate rank. How will you calculate? You have to check whether the linear independent vectors are there or not. So since rank is 1, so if you want to calculate rank, just follow this thing. 6 minus 2, 2, 0, 6. So Viveka is true here. Very nice. Okay. I'm converting into row echelon form. Minus 2, minus 6, minus 8, 2, 6 minus 2. I'm first calculating R2 is equals to R2 minus 3R1. Okay, let's do this operation. Then it is 0, minus 2, minus 6, minus 8. And then 2 minus 6, this is minus 4. Okay, 2, 2, 2. Okay, now this R3 minus R1, 0, 8, 6 minus 2 is 4. Okay, yes. So you can see 0, 2, 2, 2. This is 0. Let's see. Let's scale by a factor. Suppose 0 minus 8 minus 4. This is 0, 0. You can just R3 tends to R3 minus or plus R2. Okay. So now let's try to get 0 here. 2, 2, 2, 0, 0, 0. So R2 you can write R2 plus 4 R1. Okay. You can write 0, 0 minus 4 plus 4 R1 means 8. Okay. You can write 4. Okay. So this is nothing but 2, 2, 2. This, anyway, you can make 0 here. The operation will be R2 tends to R2 minus 2R1. So yeah, since rank is 1. Anyway, this is one of the way to calculate rank in one of the easy way. Or else you can also calculate number of linearly independent vectors. Take this as a C1, C2, and C3. You just check how many linearly independent vectors are there. So you will find that only one independent vectors are there. Otherwise, there is a dependency. So that's why it's the answer is C. Or else one other way is to check the column operation. Also, you can check. Using column operation, you can check one of the things. But row operation, generally, I'm used to it. So yeah. C1, C2, and so Guru Swami is telling no. Answer is C. We can see here the rank is 1. Viveka is telling 8, 4. I don't know what is 8, 4. Okay, I think some values he is telling. So okay, I hope this is clear. So most of the time we get confused in this and we do mistake here. So don't do mistake. Try to find the rank using row echelon form.
R2 changes to R2 minus 2 R1, then 0 minus 2 R1.
Which one?
There is minus 4. How that 0 comes? There is minus 4 and 0 minus 2 R1 minus 4, then
this
4
one
minus 2 R1. The step third row, that is 2, 2, 2, 0, 0, 4, 0, 0, 0. Then you wrote that R2 changes to R2 minus 2 R1.
Yeah.
How this 0 comes in second row?
Okay. Got it.
Okay.
Last one you are telling, no? Okay.
Yes.
I assume the answers in the train. Okay, very nice. So yes, R2 doesn't goes to, if I check R2 minus 2 R1, then all these value will change.
Yes.
Okay. So rank should be 2.
2. I think.
Yeah, rank should be 2 then. Okay. The rank of A is 2. Okay. Then there should be mistake here. Rank is 1, ma'am. Viveka, rank is true. Okay, Guruswami was telling from the beginning, rank is 2. Nice. Yeah. So there is some mistakes as I'm telling. So yeah, answer is 2. So those who
Yes.
have told this,
Yes,
you
one like
check
that in
C1,
first
C2, C3.
assignment also. Some mistakes.
Yeah, some mistakes are there. No, anyway, anyway you check the rank will be 2. If it is coming from the row echelon form also, then also it will be same for both the things. Matrix will not change. Don't worry, there will be some mistakes in previous assignments also. I'm telling. So answer is 2. Answer is not 1. I also did some mistake. I ignored it just by assuming answer is 1. Okay. So yes. Moving to the next question. Now check this. Okay, so Guruswami is very fast, so he has told answer as B. Just waiting for others to check. So here is also telling B directly. Okay, great. I think we only have 8 minutes left, so I'm just moving. I hope this is clear. How will you check? How will you check whether B is a linear combination of columns of A or not? Okay, so answer is B. All of you are correct. Nice. So moving to the 7th question. Yeah, tell me the answer. At any point, if you have doubt, just stop me and we will check. We will go through everything. So answer is which of the question is which of the following statement is true? Again, some analogy from the what we have studied. Oh, so sorry. So Viveka is telling D. Guruswami is telling B. So none of these. Viveka is telling none of these. Okay. Is this? If B is in column space of A, there always exists a solution to system of linear equation. Why Viveka B is not answered? We saw, no, if we have seen by having the span, if it is in the column space means what? Linear combination of the columns of the matrix. Then I think B is also answer. B doubt, ma'am. Okay. What is your doubt? Why B doubt? There should be always a solution. Then we saw two conditions, whether it is unique or not. Then we saw how it is unique and when it is unique. Okay. So, yeah, answer is B only because C is anyway wrong. A is also wrong, and none of these I think is not an answer. Okay. So moving ahead, question number 8. It's again a composition. Just solve it very fast. Then we'll go to 9th and 10th. So okay, someone I don't need to check. So okay, so two people are telling me A. Nice. So just nothing. It's you have to put the values A1 and 2. How we will solve? G of F of 1 2. G of F of 1 2. So these are some questions which are just getting for marks. Okay. Now check this. So everyone told the answer is A. Very nice. Now check 9. What you have to check? Linear independence of rows of the matrix. Definitely this tall matrix will not have. So B cannot be an answer. Check A and C. Okay. So A. Anyone telling me C? Okay. Amir is telling me C. So 2 students are telling. Anyone else? Hiraj, Vijay Kumar, A. So majority is A. So let's see the answer. Answer is A. So definitely this column, the rows of C will be linearly dependent. Ambili, you have to check it. Just linear independent dependent will be existing. I think only 2 minutes left, so I'll just jump to the last question. If you have any doubt, just let me know. Yeah. Yes. Only last question, which is question number 10. Nice. Everyone is telling nice. Hiraj, Sampath, Guruswami. Anyone else? Ambili, Radhika, Viveka. Okay. So system has infinitely many solutions for n values of, because it is a wide matrix, definitely it will be a C option. Unique cannot exist. Definitely, there's no solution. We have seen for a right inverse case, there will be definitely a solution. Then only for a tall matrix, we have seen that there can be a no solution case, but for a white matrix, there is always a solution. So yes, I'm very glad that most of you solved the questions correctly. So yeah, I hope you enjoyed the session. I'm expecting the same, at least this number of strength in the next class also. And those who have not watched my lectures, you can watch week 1 and week 2 by giving only 2 hours of time. You can go through all the content of week 1 and week 2. Okay, thank you, Ambili, for joining. So okay, we will end the session today. Thank you so much.